So, my slides are visible, right? Slides to move.
Yes, sir.
Okay, thank you. So, good evening, everyone. I welcome you all to the week 3 live interactive session on the applied thermodynamics for engineers. So, we have already covered 2 weeks where we have talked about the basics of thermodynamics, and then we recently also covered what are the various equations that will be used while solving any numericals. And first, we have also seen the different laws of thermodynamics and also solved few numericals on them. Now, in this week lectures, we'll be dealing with properties of pure substance and if they and what are the equations that are valid while solving numericals for them, that we'll be seeing in this week. Before that, I would like to introduce myself. My name is Abhishek. I am a POMRF research scholar in the Department of Mechanical Engineering, IIT Guwahati. So, if you have any of your doubts, you can directly write a mail in this mail ID. I will be more than happy to answer you. And if you are missing the lectures, then you can find the recorded version of this lecture of these sessions in this YouTube channel. Okay, so let's start then. So in this week's we covered lecture 8, 9 and 10. So we'll be first covering the summary of what are the important aspects that were covered in this week's lectures. Now if you see, we have covered, first we started with what are pure substance. And pure substance, the definition goes like this, that it is a substance which have a uniform chemical composition throughout the system. So this definition might sound little bit confusing, but I would like to make it more simpler way. So let us take a system. If you are taking a system or a container, so we should be having same chemical composition in all the places, like at this. So A, B, C, D. So we should be having same chemical composition at all the places. For example, if you are taking, let us say, if some part of them is covered by water and some part is covered by oil, then we cannot say it is a pure substance, because we might not be having equal mixture, equal proportion of mixtures of water and oil at all the locations, due to the variation in the density. But if you are talking about air, then what we can say is air will be having almost same. Air will be having equal composition at A, B, and C and D. There might not be any variations when we are talking about a particular temperature. But as the temperature reduces or the temperature changes, there might be variation in the chemical composition. Okay. But when we are talking about phases, like let us say there is half of it is covered with water and half it is covered with water vapor, then that also we tell it to be pure substance, because everywhere we are finding the same chemical composition, that is H2. Okay. So based on that, we have two important properties were discussed. That was T saturation and P saturation. That is saturation temperature and saturation temperature. And what are these? These are the temperature. What is saturation temperature? This is the temperature at which the pure substance changes its phases. Okay. And this is the pressure at which it changes its phases. And based on that, we discussed three curves for this pure substance. Mostly this is for water vapor, water vapor. So this is the P versus V diagram. This is P versus B. This is T versus V, and this is P versus T. So these are the generalized phase change diagrams for all the pure substance. And if you see, you try to remember all this all these curves, because slightly there is a change. You can see there is a dome-like structure. In any phase change substances, you will always be finding a dome-like structure. Okay. Now, the important thing is that this point will be known as the critical temperature. We'll be learning more about this in the next slide. This is the critical temperature, above which there will be either liquid and there will be vapor, and they won't be having any phase change. There will be no intermediate phase. So direct after this point, up till this point, there will be liquid, and with the minimum amount of heat, just at fraction of seconds, it will be getting converted into vapor above critical temperature. But below the critical temperature, there is a there will be presence of phases. And this process where liquid converts into vapor, like this is where it completely converts into vapor. That is why we are telling X is quality is equal to 1, because we define quality by mass of the vapor by mass of vapor plus mass of liquid, and this is liquid. This is X is equal to 0. So from here to here, X changes from 0 to 0.1. So of course the X is a fraction, so it converts from 0 to 1 in between this these two extreme points. Now, one of the things, this dome is not symmetrical. That is also you need to understand that, because when we are talking about water, it is an incompressible substance. So whenever there is any fluid which is incompressible, you can see that as pressure is increasing, there is only minor change in the specific volume. That is why you see the slope is little bit higher. But when you come for vapor, with reduction in the pressure, there is a drastic drop in the drastic increase in the specific volume. Okay. So magnitude, like frankly speaking, magnitude wise, theta 1 will always be greater than theta 2. That you need to notice from here. And one of the things, the other thing that you need to notice is in P versus T diagram, V diagram, these curves are known as isotherms. Isotherms. That means constant temperature lines. These are the constant temperatures line. Okay. You need to see it properly, because when you will be solving some few problems, you need to remember how this figure looks like the phase change graphs looks like. So here, okay, this is the temperature isotherms. This is the constant temperature lines. Now, when we are talking about T versus V diagram, you can see here also the dome structure is somewhat similar to P versus V diagram. The slope of the saturated vapor line is slightly lesser than the saturated liquid line. And when we are talking about the constant, here you will find isobars or constant pressure lines. These are the constant pressure lines, and you will find that these are having opposite. It is a little bit opposite to the isotherm graphs. And this is the P versus T diagram. This is also will be helpful while solving some problems related to the triple point. This is the triple point where all the phases coexist at the same location. Okay, you can at this location you will find solid, liquid, and vapor, and this curve is for the substance which expands on freezing, somewhat like water. Okay, that is why you will find that ice density is lesser than water, and thus ice floats on water. Okay, and this is the curve for this is the melting curve for the any substance which contracts on freezing, like many other many other liquid to solid. Many solids you will find that when they get converted into liquid, their density will be increasing. Okay. So after that, lecture number 9 and 10. And when we are talking about these vapors, mostly we will be dealing. Water is one of the most widely used or widely used substance around any chemical composition or any power plant. If you say if there is any Rankine cycle running, so we use water. So that is why it is very important for us to know its properties. and whether we can use those properties directly or whether we need to use some tables, that is what is decided through this graph. You can see that for this is for the water compressibility T versus V diagram for T versus V diagram, T versus V for water. Okay, and you will find that whenever the pressure at low pressure and high temperature, extremely high temperature, it almost behaves like an ideal gas, and thus here we can use ideal gas equation like PV is equal to RT. Okay, so P into small v is equal to RT. We can use it in this result. But when we are coming to this location, we have to know the properties, and for that we use steam tables. And I hope you might have followed these lectures and where we have learned how to see the steam tables. So basically you will be having two tables. One is saturated table, in which either you need to saturated table where the first column will be mostly pressure or temperature. If it is given pressure, this is actually the P saturation. The second will be T saturation. Second column will be T saturation, and all the properties will get after that, like V, U, H, and S. All the properties you will find in this saturation table. But when we are coming to any superheated table, it will be different for each pressure. Let us say this will be somewhat around 3 megapascal and 500 degrees Celsius. So at 3 megapascal, the table will be different. It will start from its T saturation. First row will be given its T saturation, and after that the temperature will go on increasing. I hope you have understood it from the lectures, and while solving few numericals also we'll see how this table is used. Okay, so in that cases we'll be using the property tables. Now, whenever we are using, if the gas if we don't have the property tables and we cannot use the ideal gas equation, there are some other equations we try to use. Those are somewhat like van der Waals equation. Van der Waals equation. Which says that P plus A by V square is equal to V minus V is equal to RT. These are small v, of course, specific volume, and this A and B is somewhat like this. Please remember this formula because we'll be also solving one problem on this. So A and B are solved like this, and they are derived by, at the critical point they are equated, their derivative is equal to 0. P by dou V at critical point is made to 0, and dou square P by dou V square at critical point is equal to 0. Using these two, we solve these two unknowns, okay, at the critical point. So, and based on that, we can calculate the property of various substances, like for example, if oxygen or nitrogen is given, where we don't use any tables, property tables. There we can use this van der Waals equation based on certain how much error we are getting. Based on that, whether we can use van der Waals equation or other equations like Beatty-Bridgman equation and Benedict-Rubin equation. These equations are a little bit hard to remember, and of course, if there any question comes, then mostly it will be given in that question. Okay, so I hope this much summary is enough to wind up this week lectures. So based on that, now we are going to solve the numericals for this week. Okay. So here it goes. So the first question is, among the following substance, which one is true? For a substance which expands on freezing. As I said, to remember all the curves, that curve will be useful here to solve. It will be solved through, see, expands on freezing. This is one of the keywords, and there is in option it is given triple point. So I hope now you can understand which curve to use, that is P versus T. Okay. And I'm giving you a few minutes. Try to make the P versus T diagrams in your copy and try to answer this question. Are you solving? Vijay?
Yes, sir.
Yeah, give it a try. If you could draw the P versus T diagram, then you can solve this question. It's very simple.
Okay, sir. This is the triple point diagram.
Sorry?
Triple point diagram.
Triple point? What? What is triple point you are asking?
It's
It is the state where all the three phases like solid, liquid, and gas coexist. Okay.
yeah.
Can you draw the P versus T diagram? If that you can do, then this question becomes very simple.
Yes, sir.
Yeah, just draw it. Then you try to see all the options, which is true. That one you tell me.
Okay. Option A is correct. Option A.
How does it look like? It somewhat looks like this. This is the, let us say, the triple point. Then it goes like this. And this is for which one expands on freezing. So there will be two curves. One is like this. It will be slanting towards the T axis, but which expands, it will be like this. Okay.
अरे क्या है
Okay. This is solid, liquid, vapor. This is the triple point. This is how it looks. I have covered here. You can see this is the curve I am talking about.
Yes, sir.
Now tell me. First option. What is first option? It can stay as liquid below its triple point temperature. So first of all, which is this is the triple point temperature.
Yes.
This is the triple point pressure.
You value this.
Okay. Then tell me below the triple point temperature, whether it can exist as a liquid or not. So below the triple point means
Below the triple point
it is talking about this region.
Exponent region.
Okay, it is talking about this region. In this region, whether liquid is existing or not. You tell me yes or no. Huh? Are you able to follow? Are you able to understand or not?
Solids, solid.
Array,
Hello.
yeah, tell me.
Solid phase, no?
Below this line there is solid, but liquid is this whole region from here to here. This is the critical point. So it is existing here or not? This is the reason where below the critical temperature you can find liquid. Okay. So first one is correct. We'll see whether B, C, D are correct or not. Next point is it can stay as liquid below its triple point pressure. Below its triple point pressure means I am talking about this region. Below this curve. Below this curve. Whether it can exist as triple point. It can exist as liquid below this point. Yes or no? Tell me. Are you having any confusion or what? Because you see it is very clear below this pressure, below this line, whether you can find any liquid region. Liquid region is above this point. It's not below this. So option B is wrong. Then option C is it can stay solid above its triple point temperature. It is correct or not? Above its triple point temperature. So do you find any solid region above the triple point temperature? In this region, are you able to find, are you finding any solid region? No, right? Because you can only find liquid and vapor region. So C is also wrong. Coming to D, it can stay as vapor below its triple point pressure. Okay, it can stay as vapor below its triple point pressure. Whether it is true, below the triple point pressure is this one. Okay, this region. Okay, so whether it can stay as it cannot stay as vapor below its triple point pressure. So we can find that this is the region where vapor is there. This is the vapor region. This is vapor.
Yeah.
This is liquid.
Yeah.
So it can exist. So even D is wrong. So the correct answer is A. Okay, are you able to follow it? Did you follow it?
Yes, sir.
Okay, we'll move to the next question. Compressibility factor for an ideal gas is Z. It is asking for Z value. For an ideal gas, what is it? It is very simple. Just tell me. Z is PV by RT.
Compressibility factor for
Compressibility factor for an ideal gas is what? Whether it is 0, it is 1, correct. Because ideal gas equation is PV by RT. PV is equal to RT. So when you these both are equal, so when you take their ratio, it is 1. So compressibility factor for an ideal gas is 1. Then the next question: a real gas is likely to resemble the ideal gas behavior at what? This one we just discussed few slides back. Just tell me. When does a real gas behave as an ideal gas?
At low pressure and high temperature.
Okay. Real gas. Yeah. So this is at low pressure and high temperature. So which option is correct? Option C. Okay. Coming to question number 4. Density of a sample of water is found to be greater than the density of saturated liquid at the same temperature. Then the thermodynamic state of this sample is. Tell me. You can take help of any of the curves. It is you can use whether P versus V, T versus V. Mostly between the PV graph or TV graph, you will get the answer for this question. Tell me. I'm giving you a few minutes. Think about it.
Whether it is a compressed liquid, sir.
Your voice is not clear. If you're asking something, I am not audible. It's not audible. Take the help of this curve. P versus V or T versus V. Both of this you can take help of that and think about it. It's talking about density.
C option.
Specific volume. It's a reciprocal of density.
Yeah, correct. Reciprocal of density is specific volume. It's P or T. Let us say it is V. So you're going on the right direction. Just think and tell me what is the answer.
The saturated liquid line is the two left hand side saturated liquid line.
Correct.
Yes, sir. But the given density of sample water is found to be greater than the density of saturated liquid. Now,
Okay. Correct.
greater than in the sense its specific volume is lesser
Correct.
than the specific
Very
volume
good.
of the saturated liquid.
Yeah. Then what?
It goes in a compressed liquid state, sir.
Yeah, its correct answer is compressed liquid. How it is, just I'll see. This is the reason for compressed liquid.
Yes, sir.
This is liquid plus vapor, and this is vapor. Okay. Now it is telling that density, we are taking a sample and that sample's density of that sample is greater than density of saturated sample is greater than the saturated water density. Okay, so let us take the reciprocal of it. So its specific volume density is reciprocal is specific volume, sample will be less than specific volume of saturated water. So now tell me which is the here. This is the saturated volumes, specific volume of saturated water. Okay. Now, who's if a sample having the specific volume lesser than this, then which state it is? It is compressed liquid. So option A is correct. Did you understand?
Yes, sir.
Yeah. Coming to next question. Yeah. Some quantity of water is supplied with 10 megapascal pressure and 0.03 meter cube. This is meter cube per kg, specific volume. Meter cube per kg, specific volume. The thermodynamic state of the sample can be identified as. Mind you, you have to use a little bit of steam table in this question. So if you have steam table somewhere near you, just bring it and use it. I'm giving you a few more minutes. Try to solve this question. These are all fundamental questions. So solving these questions will really help you to understand the subject.
Yes, sir. I have referred the steam table.
Okay.
Specific volume at liquid that is equal to VF that is equal to 0.001452 at
Correct.
10 megapascal 0.001452 meter cube per kg.
What is the VF you are getting? Just I will also refer. Yeah. At 10 megapascal. So mostly your steam table will be having in kilopascal, right? So you have to check for 10 into 10 to the power 3 kilopascal. Okay. So 10 into means 10 megapascal means 10,000. Okay. So just check at 10,000 how much is the specific volume? Yeah, he was you are
0.001452 0.001452 meter cube per kg.
Correct. At 10 megapascal, VF is equal to, from steam table, of course from steam table, I am referring the steam table of Cengel and Bose. So that is, yeah, so that is table number A5. Table A5. So VF is equal to 0.001452 meter cube per kg. What is VZ? VZ is
0.018028.
correct. 0.018 0.01808 meter cube per kg. Okay. Now what is it is telling? The specific volume of this quantity of is we are having given V given is how much? 0.003 meter cube per kg. Okay. So if I draw one, in such questions try to draw every time you try to draw a curve, whether it's P versus V or P versus T. It will look somewhat like this. Okay. So in one case, let us say this is the 10 megapascal pressure. Okay. This is VF. This is VG. Okay, because this is the saturated line. Okay, I hope you understand. So this is the saturated line, saturated water line or saturated liquid line. saturated vapor lamp. Okay. So here this value is telling it is 0.001452 and this value it is telling 0.018028. So now tell me whether 0.003 will be existing in between this. Just I will mark at point A, point B or point C.
That's point B.
Yeah, correct. So it will be somewhere here. 0.003 meter cube per kg. So what is the condition? What is the within the dome? What is the region called?
Saturated liquid vapor mixture.
Mixture, correct. So our answer is C, saturated liquid vapor mixture. For example, if the specific volume would have been given, let us say 0.0010, then it would have been compressed liquid. It would have been at point A and it would have been compressed liquid. And if it would have been greater than 0.018, then it would have been vapor. Okay, I hope you understood. Now we'll go into some numericals now. Okay, try to solve this question. Vapor pressure of solid ammonia in mm of mercury is given by ln P 23.03 minus 3754 T. That of liquid ammonia is given by ln P 19.49 minus 3063 T. Here P is in mm. P is in mm of mercury and T is in Kelvin. The temperature of ammonia at the triple point is. So we have two state. Let us not tell state. We have state equations. Solid ammonia follows ln P is equal to 23.03 minus 3754 T. Liquid ammonia is ln P is equal to 19.49 minus 3063 T. Now it is asking what is the temperature of ammonia at triple point. So all the things, some of the key words are already mentioned. Try to find them and solve this question. I am waiting for you. First solve the question, tell me the answer, then we can discuss what was your approach and how did you solve it.
The triple point existence of solid, liquid as well as vapor is possible.
Correct.
That's why that ln P is equal. If you are equating this equation 1 and 2,
Okay.
we can get the temperature, sir.
Yeah, that is correct. So your approach is correct. Try to solve this problem and tell me what is the answer you are getting. I will also check.
Actually, sir, I'm getting temperature in the order of 10 power minus 3. I hope so. Here, ln P 23.03 minus 3754 divided by temperature, or that is multiplication, sir.
Okay,
Whether it is
just I'll check
multiplication.
once. Yeah, maybe that might be a mistake.
Oh,
Just I'll check. Yeah, it is divided. You are correct. Very correct. Sorry for that. So it is divided by T.
by that time, I am getting 195.2 Kelvin, sir. 195.
Okay, so you are getting T triple point is 195.2. Kelvin.
Yes, sir.
Let's see. So as said, it is very correct that at triple point, all the phases solid, liquid and gas coexist. Okay, so if they coexist means their state points will be same. State points, this implies that state points will be identical. That means pressure and temperature in solid state must be equal to pressure and temperature at liquid state. So that is what you have to equate. So ln P is equal to 23.03 minus 3754 by T. Okay, you equate both of them. So 23.03 minus 3754 by T is equal to 19.49 minus 3063 by T. If you calculate that, just bring it to one side. So 3754 minus 3063 by T is equal to 23.03 minus 19.49. T is equal to it is 195.12. 195.19 Kelvin. Okay. And yeah, so you are correct. So it is 195.19 Kelvin. I hope you understood. We'll move on to the next question. A vessel of volume 0.04 meter cube contains a mixture of saturated water and steam at temperature of 250 degrees Celsius. The mass of the liquid present is 9 kg. Find the pressure, the mass, the specific volume, enthalpy, entropy, and the internal energy. So this is a very fundamental question for how to use the steam table. So go for it. Try to solve this question.
Procedure is if you refer the temperature table and take all the properties
Do it.
DF.
Yeah, you do it, then we'll discuss.
I have calculated the volume of liquid. Mass
Okay.
of that liquid is given 9 kg. I have taken that specific volume value from the steam table,
Okay.
and I multiplied that mass with the specific volume.
Okay.
Uh, the total volume of liquid is around the 0.1126 meter cube. Here total volume of the vessel is given. From this we can calculate the volume of vapor.
Okay.
The remaining is volume of vapor. Once
Correct. So
volume of vapor
yes.
we know, in the sense we can find the mass,
Correct.
because volume of the gas, uh, volume of the vapor divided by specific volume.
Okay.
We can get the mass of the vapor.
Mm.
Already mass of the liquid is given.
Okay.
Mass of the liquid plus mass of the gas
Okay.
vapor.
Mm.
Then we can get the total mass.
Okay.
Uh, then after quality of the mixture, uh,
Okay.
the dryness fraction value we can calculate.
Okay.
You know the mf, and then mg divided by mf plus mg.
Okay.
And thereafter it is a wet condition, in the sense enthalpy, wet steam enthalpy, HF plus X into HFP, SF plus X into SFP. Once we know that enthalpy, then we can calculate the internal. Okay.
Okay.
Now,
So
what is
okay. So I understood your approach is perfectly right. So have you solved all the bits? Like, have you got the values?
yes, sir, specific volume.
Okay.
Um,
If you have got, then we'll check. I will also solve. So we'll check.
okay.
So yeah, so I will just explain how to solve this question. So it is saying that a vessel of volume. So we have a vessel whose total volume is given as. Please, whenever you solve this type of question, always remember whether the volume is given or specific volume is given. That is very important. So the volume is given as 0.04 meter cube. Okay. So first of all, we are having a vessel of this much volume. Then it is saying that it is containing a mixture of saturated water and steam. Okay. So both water plus steam is there inside this. And what is the temperature it is telling? 250 degrees Celsius. So now, as we are getting to know that this is we have to see the saturated table. Saturated table. Saturated steam table. And let's see. Okay. From saturated steam table, if I see then a temperature, so we'll be referring to the table. You will get some table like this, in which the first column is T, T sat. Okay, T saturation. There you find for 250 degrees Celsius. For 250 degrees Celsius, I am getting a value of at 250 degrees Celsius. You will get this in table A4. Table A4 of Cengel and Bose. Cengel and Bose. At 250 degrees Celsius, you will find P saturation as 3.976, 3.9762 megapascal. Yeah, megapascal. Am I right? So this is the pressure. Find the pressure. So first bit is done. Okay. Now the next thing is, see what is saturated liquid volume, VF. I am getting it is around 0.001252. 0.001252 meter cube per kg. And in the question we have been given the mass of the liquid present is 9 kg. So we have mass MF is 9 kg. So can we calculate total volume is equal to mf into vf, total volume acquired by the liquid fraction. So let's calculate that. So I am getting 0.011268 meter cube. Okay, so this much is acquired by the liquid. Then what is the remaining? Vg is equal to 0.04 minus 0.00, sorry, 0.011 0.011268. Is 0.028 meter cube. Correct? This is the total meter cube acquired by the gas. Now, once this is done, can you calculate what is the specific? We can get the specific volume from the steam table. What is the specific volume? At 250 it is 0.05, 0.05, 0.05, 0085, 0085 meter cube per kg. So can we calculate mg then? Of course we can do. We have to just divide them. Plus weight divided by 0.050085. I am getting 0.55 kg. 0.559. Am I right? Is this what you are getting as the mass of the gas?
Yes, sir.
Okay. So once that is done, so you have both MV, you have MF and MG. So can you calculate now quality? It is nothing but Mg by MF plus Mg. I am getting 0.058. Are you also getting this one?
Yes, sir.
Okay. Once that is done, now calculate enthalpy. Enthalpy is equal to HF plus XFG. So all of these values you can find out from the table. So where HF is, I am getting 1085, 1085.7 plus 0.058 into 0.058 into 1715.3, 1715.3. In some tables you might not get HFG value. There what you can do is HFG is equal to HG minus HF. That you can do. And once you put these values, you put 058, 1715.3 plus 1085.7. I'm getting 1186. 1186.01 kilojoule per kg. Okay. And if you want also directly enthalpy, this is specific enthalpy, and if you multiply the total mass M1 plus M2, MF plus Mg into 1186.01, 1.559. You get, I'm getting somewhat around 11.337 megajoule. Correct. This will be capital H, specific volume. Similarly, entropy also you can calculate SF plus XFG. This one you can take it from the table, and internal energy U is equal to UF plus UFX into UFG. Okay, correct? How much are you getting entropy?
Around 2.98 kilojoule per kilogram Kelvin.
2.98 kilojoule?
9 kilojoule per kilogram Kelvin.
Kilojoule per kg. Kg is not there, right? This is just entropy.
Kelvin. It's kilojoule per kilogram Kelvin.
So you have not multiplied with 9.559. No. This is specific entropy, right? Huh?
Yes, sir. Yes,
Okay. Then what is the U that you are getting?
Entropy is around 28.62. 28.62.
Yeah. So you are right. I'm also just checking. So entropy is specific entropy is 1171.71 kilojoule per kg. And if you multiply with 1171.71 into 9.559, you are getting 1849. Sorry. 1171.71 into 9.559, think 11.2 megajoule. Okay. I hope you understood this question. Correct? You understood, right?
Yes, sir. One more subdivision, the specific volume of the mixture also we need to find. Am I correct, sir? Find the pressure, calculated mass, the specific volume of the mixture.
Yeah. You can directly like MFBF plus MGVG by MF plus MG. Okay. I think this should give them the mixture, specific volume of the mixture. Correct?
Okay, sir.
Otherwise, you can directly, same thing only, V is equal to VF plus XVFG. Because when you divide this MF plus MG, it will finally get converted to this equation. Am I right or not?
Right, sir.
To the next question, did we skip here? Water at 120 degrees Celsius with quality of 0.25 is heated till its temperature rises by 20 degrees Celsius in a constant volume process. Its new quality will be. This is a good question. Test both your fundamental and also concept. So try to answer this question. Solve the question and then tell the approach.
here initial temperature is 120 and the quality is 0.25.
Okay.
For this, we can find a specific volume,
Okay.
Vf plus x into Vfg. And
Okay.
then the temperature is rises by 20. That is
Okay.
120 plus 20, 140 degrees Celsius.
Okay.
Here, constant volume process is mentioned here. That's
Just
why specific
okay.
volume.
Okay. I can understand that your approach is right with respect to solving the numerical. Without seeing the stream table, can you tell me whether the quality will be coming more than 0.25, will be coming less than 0.25? Without solving anything, just if I ask it as a multiple choice question, if water at at a certain temperature is heated of this quality is heated at a constant volume, so whether it will increase or whether the quality will increase or quality will decrease.
I have calculated, sir. I am getting the quality is what it decreases. Instead of 0.252, it comes down to 0.2122 like this.
Is it? We'll see. Now you tell me, the without solving, if I ask it as a multiple choice question, whether the quality will increase or quality will decrease if we hit by constant volume process. What do you think? That is why I am saying always try to
Temperature
remember the
volume diagram. Temperature volume diagram. By referring the
correct.
temperature volume diagram, we can get ideas of it. So initial
No,
temperature
I
this
will
will be.
no. That is what I am telling. Temperature volume diagram you can refer, but I will not give you any values. I will just give you the specific volume value. Let's see. You will yourself will tell the answer. So T versus V. So this one, no, this one is more slowly. Okay. Okay. So this is the temperature. This is 120 degrees Celsius, and this is 140 degrees centigrade. How does the constant quality lines look like? This is the critical volume, critical pressure, critical part. Okay. Now tell me, how does a constant quality lines look like? Constant quality line. How do they look in this?
Parallel to that saturated vapor line.
Correct. Very good. So this one is x is equal to 1 and this one is x is equal to 0. So let us say I will draw now x is equal to 0.9. So how it will be? It will be somewhat like this. This is x is equal to 0.9. And let us say this one is x is equal to 0.1. Okay, so similarly x point 0.8, it will be like this. X is equal to 0.8. Now let us say we are somewhere here, and if we draw this constant quality line, let us say this is x is equal to 0.7, and when we hit now at constant volume, that means it will be a straight line parallel to T Okay. So the quality increases or decreases?
Increases.
Increases. Correct. So in this case, we are finding that first case, the quality is increasing. Is increasing. Now tell me one case. Now this is, let us say, I will draw one more curve. This is x is equal to 0. Let us say 3, and we are somewhere here. Now, if you are hitting it, if you are hitting here at a constant volume, it will reach here. Let us say that same 20 degrees Celsius we are hitting now, and we are hitting to reach it here. Now you tell me whether the quality is increasing or decreasing.
Decreasing, sir.
Decreasing. Correct. This is the second case. Second case, quality is decreasing. Now, what is the basic difference between both of this position? Tell me. What happened that suddenly the quality, while hitting, the quality is reducing? Tell me.
Nearby the saturated liquid line, right?
Not nearby, no, don't tell like how much near. When someone asks how much near, how much, you just see the curve, just analyze the curve.
Of the critical point, left hand side of
Correct. So that is perfect. So if this is the critical volume, specific volume at a critical point, let us say this is some value. If we are going on the left hand side, if the specific volume is reducing below that, then we can say that the quality will reduce on hitting, and if we are on the right side, then the quality will increase. Okay, so that is the case. Now for this case, now we'll do the calculation. Now what are the critical values of water? Try to remember always. We'll be seeing one more question is also there on this, and you will get the values. Try to remember that, so that sometimes this question can come as a multiple choice question and they would not give you anything, and just you have to analyze and tell. So just remember that if the specific volume is lesser than the critical volume, so this is the case. If the specific volume is more than the critical specific volume at the critical point, then the quality will increase, and if it is less than the critical volume at specific volume at the critical point, then the quality is decreasing. Sorry, this is decreasing. Okay. Now let us do the new solution. As you said, at 120 degrees Celsius, we'll see what is VF. Just I will refer the table, the same table, table A4. A4 120 degrees Celsius, I am getting 0.00, 0.0010 1060 meter cube per kg. Vg is how much? 0.8913, 0.8913 meter cube per kg. Okay, and again, so calculate the specific volume. So 0.8913 minus 0.001060 into 0.25, we are getting as 0.22 plus 0.001060. So I am getting specific volume as 0.22362 meter cube per kg. Okay. Now it is heated by 140 degrees Celsius, and we are telling that it is at constant volume. Okay. So let us say this is V1, and we'll equate it with V1 is equal to V2. Okay. So at V2, at 140 degrees Celsius, what is at 140 degrees Celsius? What is the VF? VF at 140 degrees Celsius? I'm getting so all this I am seeing from table A4. Table A4 of St-Gelland rules. So VF I'm getting 0.001080, 0.001080 meter cube per kg. Vf is equal to Vg is equal to 1 at 140 degrees Celsius is 0. How much? 50850 meter cube per kg. Be careful about the units. So V at 140 is equal to how much? 0.5085. So we will calculate this. So 0.001080 plus x into 0.50853 minus 0.001080 is equal to 0.22362. Equate this 0.22362 minus 0.001080 divided by 0.50853 minus 0.001080. I am getting x is equal to x2. x2 is equal to 0.438. So it has increased or decreased?
Now
It has increased. Yeah.
Yes, sir. The concept is correct only because the critical specific volume is 0.00317, 0.00317 meter cube per kg. Initially, we are getting V1 as 0.22362. It is ahead of 0.00317. So
Correct.
now when we started to PT, definitely the quality will be improved. So now it is improved from 0.25 to 0.43.
Correct. Correct. So you understood the concept, right?
Yes, sir. Thank you, sir.
This is very important. If you are taking some notes, just write it. Okay. Now we'll move to the next question. An isentropic steam turbine receives 2 kg per second of steam at 6 megapascal and 500 degrees Celsius and lives at a pressure of 0.3 megapascal. If the expansion process can be assumed to be isentropic, then the work output from the turbine is how much megawatt? In megawatt you have to tell. So this is very simple question. I am giving you 3 minutes. Try to solve this question and tell me.
Yes, sir. Our output, which is equal to mass into change in specific volume. Specific
Correct.
volume at inlet 6 megapascal, 500 degrees Celsius. It is
Okay.
at superheated condition. Superheated
Correct.
table we need to refer, and we need to get H1 as well as entropy S1 because isentropic condition. So S1 equal
Okay.
to S2, and
Okay.
then we need to get the quality of steam at the exit from the turbine H2.
Okay.
After finding H2, we need to find if it is less than 1, that is what the wet steam, then H2 equal to HF2 plus H2 HFG2. We need to refer from a saturated table 0.3 megapascal, 0.3 into 1000, the kilopascal value. And then,
Okay. So your approach is totally correct. So did you solve the question? Try to
yes,
solve
sir.
this one. Yeah. Solve it, then we'll discuss. And then we'll check, cross check.
Around 1.49 megawatt. Let us check, sir. Again I cross check the value 1.49 megawatt.
So let me start. So It is some of the any question will be having some keywords and we have to follow them. So it is saying that an isentropic steam turbine. So first thing is isentropic, then it is steam turbine. So from both of this we know that if there is a turbine means there will be expansion. If there is an expansion means there will be pressure drop, and that is what we are seeing here from 6 megapascal to 0.3 megapascal. Okay. If it is isentropic, that means S at the inlet of turbine is equal to S at the outlet of the turbine. That's all. This much if we get. What will this, how this will help? Because at this location at 6 megapascal and 500 degrees Celsius, you will find that it will be saturated condition. How? Let's see. Now at 6 megapascal, T saturation is how much? We'll see that. Okay. So I'm referring table same A5 at 6 megapascal means 6,000. I'm getting 275.59 degrees Celsius. This is the T saturation, but our temperature is greater. It is 500 degrees Celsius. That means it is superheated steam. And mostly always the turbine's outlet will, when we'll study the power plant, we'll be getting to know that turbine's inlet will be mostly it will be in dry state, that is in superheated state. So that after expansion, it should be close to the saturated vapor lines. So that if any water vapor is there won't be any, if there is presence of water vapor, there might be corrosion. We will see them in the Rankine cycle when we are going through the Rankine cycle. We'll surely go through that. So for now, we have superheated state at 500 degrees Celsius and 6 megapascal. So let's refer to the superheated table. Superheated table 6 megapascal. I'm going for table 6. Table 6. Table A6 of Cengel and Bose. Cengel and Bose at 6 megapascal at 500 degrees Celsius. I have to find out what is H1 and what is S1. So H1 is 3423.1. I hope you are getting this value, 3423.1 kilojoule per kg. And S1 is 6.8826. 6.8826 kilojoule per kg. Okay. This is at 6 megapascal and 500 degrees Celsius. Now this is at the inlet of the turbine. Now let's come to the outlet. What is the state point at the outlet? Only pressure is given because we don't need anything else. It is mostly, if it is at the outlet, it will be in saturated condition. So let us refer to at 0.3 megapascal. What is SF? What is SG? Let's see that. At 0.3 megapascal. Again, I am referring to table A5. 0.3 megapascal means 300 kilopascal. So at 300 kilopascal, it is 1.6717 kilojoule per kg Kelvin. SG is 6.9917 kilojoule per kg Kelvin. So now SF plus XF SFG is equal to 6.8826. Now from here find out X. X is equal to 0.979. I'm getting this much. Are you getting this much? Quality of the steam at the outlet of the turbine?
Yes, sir. Correct, sir.
Okay. Now let us find out enthalpy. So mostly you will find if I draw the TS plot. It will be somewhat like this. Okay. This is 1, this is 2. Now what is the work done? Work done is nothing but m dot h1 minus h2. Now h1 we know how to calculate h2. H2 we have x now, so hf plus x into hfg. Take all these values from 300 kilopascal rho. So that is I am getting 561.43 561.43 plus 2163.5 0.979 into 2163.5. I am getting H2 as, let me write it here, 2679.49. Am I right? Kilojoule per kg.
Yes, sir. Correct, sir.
So m dot is 2. So H1 is 3423.1. 3423.1 minus 2679.49. I'm getting 1487.2 kilojoule. That is equal to 1. Sorry. That is equal to 1.48 megajoule. Are you getting this much? I hope you are getting this much. Yeah.
Flow rate actually gigajoule per second megawatt. Yes, I'm getting 1.49. Correct, sir.
Megawatt. Sorry. Yeah. This is of course kilojoule per second, megajoule per second. Yeah. Next question. A pressure gauge on 1.2 meter cube per 1.2 meter cube oxygen tank rates 500 kilopascal. If the temperature is 24 degrees Celsius and the atmospheric pressure is 97 kilopascal, then the mass of oxygen in the tank is how much kg? So I have given you the compressibility chart. That means you can use the ideal gas equation, but you have to add one term, that is Z. Now how to find out Z? You have to use this chart. Although in this chart there oxygen is not given, but you will get a small hint when you try to solve it. So first of all, what you have to do, just think about it. Just I am giving you 2 minutes.
Your gauge pressure as well as atmospheric pressure is mentioned. Total pressure which is equal to gauge pressure plus atmosphere.
Okay.
And that is the total pressure.
That one will come later. That one will come later. You just tell me how to calculate the things. How to start. I can understand that in PV is equal to in ideal gas. I hope you all know, you might be knowing it. PV is equal to, if I am solving PV is equal to MRT, T is in Kelvin, P is absolute pressure. Always try to remember this, absolute pressure. And mostly this will be in kilopascal. And so then only you can use here 8.31. Always try to remember, because this will be kilojoule per mole Kelvin. This one will be kg, this one will be in meter cube. This will be always be absolute pressure, never gauge pressure. You cannot put gauge pressure in this formula. So that one I can understand that first you will calculate absolute pressure. Absolute pressure. Absolute pressure is 500 plus 97 is 597. 597 kilopascal is the absolute pressure. Okay, what after that?
R, which is equal to R universal divided by molecular weight of oxygen, sir.
Sorry?
Here, gas constant R. Here
Oh, correct. It is, sorry, this is of course the molecular weight of the gas. Actually, this is in number of moles. If it is, then you have to divide by mg. If m we are using, if you are using n moles, then directly you can write 8.31. So, can you solve it? This question?
Without considering correction factor and the m equal to PV by RT, if we are substituting here, it is 9.284.
But you have to get Z. No, that is what I told you. You have to find out compressibility factor. That is why I given the chart. How to find out compressibility factor? You need to find out PR and TR. PR and TR. What is PR and TR? What is PR? It is called as reduced pressure.
Reduced pressure, reduced.
Correct. And how to calculate reduced pressure?
The pressure divided by its critical pressure, sir.
Correct. So calculate what is the PR. So for critical properties, try to refer table A1 of Cengel and Bowles. So oxygen's critical pressure is I am referring this table. It is 5.08 megapascal. 5.08 megapascal, and critical temperature of oxygen is 154.8 Kelvin. 154.8 Kelvin. Now calculate PR. This is of course P absolute. So is 597. Remember it is kilopascal. It is 5.08 into 10 to the power 3. It is 0.11. Are you solving?
Yes, sir. 0.11, sir.
Okay. Now the temperature is 24 degrees Celsius. What is 24 degrees Celsius? You have to convert it to Kelvin. It is 273.
Temperature 1.94.
Reduced temperature. Okay. 154.8. getting 1.92. Okay. So now two things, PR and TR. So TR is 1.92 means it will be somewhere.
24 degrees Celsius. Okay.
Sorry.
Got it, sir. Got it.
Yeah.
Okay, sir. Understood.
Okay. So TR is somewhat near to 2. So it should follow this curve. Almost I am telling. Although this curve is not for oxygen, it has not been given. So it should be somewhat here. In this curve. Then other thing is PR is 0.117. So 0.117 will be somewhat here. This is x-axis is the PR. This is 0.5 means 0.25 will be in the middle, and even inside that will be 0. Here, somewhat here. So we can say that Z is almost equal to 1. So you can directly use PV is equal to MRT. So 597 kilopascal. Volume is given 1.2 is equal to M. R is 8.314 divided by what is oxygen's molecular mass? 32. Into temperature is 297. Calculate what is M.
The 9.3 kg, 9.3 kilogram.
Yeah, I am getting 9.2, 9.28 kg. Correct? Just I will check. Yeah, so 9.28 is correct. So we'll move to the next question. You understood, no? The approach?
Yes, sir.
Is the next question. So this is somewhat like the question that we have discussed. At a 1 meter cube tank contains 2.841 kg of steam at 0.6 megapascal. Using critical properties of water, which I have given here, and the van der Waals equation of state, the temperature of the steam can be calculated to be how much? So what is van der Waals equation? P plus AY V square. This is of specific volume. V minus B is equal to RT. So now you calculate. 1 meter cube tank contains 2.8 kg of steam. So what is specific volume? First of all, calculate specific volume is 1 divided by 2.841. This is not that tough question. I think you will be able to understand. It is 3.519 meter cube per kg. This is the specific volume, and at 0.6 megapascal, that is 600 kilopascal. Using critical properties of water, that means we have to find out A and B. What is A and B's formula? This is a bit difficult. I hope you might be remembering. A is 27 R P critical square by 64 P critical, and B is R into T critical by 8 into P critical. Now calculate. Remember to use Kelvin. So 27 into 8.314. I think it is R square, yeah. 27 R square T square. Yeah. 64 PCR. 8.3 square into T is 374.14 degrees Celsius. So 374 0.14 plus 273.15 is 647.29. So TCR is equal to 647.29 Kelvin. So 647.29 by pressure. Pressure try to use in kilopascal. So 22.064 into 10 to the power 3 into 64. How much A you are getting? Tell me fast.
Sir, here R is for steam. R equal to R universal by molecular weight of steam 18.
No, this is universal gas constant.
Universal gas constant. Okay.
Yeah. 27 into 8.314 whole square into 647.29 whole square divided by 22,069 divided by 60. I am getting 548. Just check the units, okay? How much are you getting? Are you getting the same? Once you get A and B, you have V. V is there, P is there, R is there. We need to find out T.
Here the specific volume value, I think so, 0.3519, isn't it, sir? Because 1 divided by
Yeah, correct. So 0.35, yeah. A and B value is correct, no? Did you calculate A and B?
Sir, doing it, sir.
Yeah, just complete it because we have a few more questions left. Divided by 8 I did do. So it's 8 divided by 8 is 0.03. Okay, these are just direct formula based questions. I think you can calculate, not a problem for you. Okay, shall we move ahead?
Okay.
Yes. So we have this question. A large insulated vessel is divided into two chambers. This is also a very good question. a large insulated vessel is divided into two chambers. So this is the chamber division. One is containing 5 kg dry saturated steam. So what is dry saturated steam means? Quality is 1 at 0.2 megapascal, and the other is 10 kg steam at x is equal to 0.8 and 0.5 megapascal. If the partition between the chambers is removed and the mixed thoroughly and allowed to settle, find the final pressure, steam quality, entropy change in the process. Tell me. So it is insulated. It's a very good question. I am sure that you will find such type of question in any of your exams.
After mixing here M1 into H1, we need to do the energy balance. M1
Okay.
H1 plus M2 H2, that is
Okay.
equal to M1 plus M2 H3.
Why H? Where did enthalpy come from? This is not the ideal gas. In ideal gas also, I don't think H will come. First of all, large insulated vessel. So total volume is constant. That you keep in mind. So just such big question and difficult question. No? To start with, a large insulated vessel is divided in two chambers. So in one chamber, we are what we are having is saturated steam, dry saturated steam. So whatever Vg will get, and if we will multiply with M is there, Mg into Vg, will get V, right? So one set volume will get. Okay. So first start with that. 0.2 megapascal dry saturated. So 0.2 means 200 kilopascal. 200 kilopascal. I am having Vg is equal to 0.88. 0.88. 0.88578. Again, I am referring table A5. Meter cube per kg. So here it is 5 into 0.88. Do this one.
4.4. 4.43 kilogram. Volume.
0.88579. 4.42895. This one is the volume meter cube. This is the one, chamber 1. Now chamber 2, V2. This is that 0.2 megapascal. Now at 0.5 megapascal. Means 500 bar. So 500 bar I am getting 0.5 V is equal to 0.001093 plus 0.8 multiplied by 0.8 0.41392 0.41392 minus 0.001093. Correct? 0.41392 minus 0.001093 into 0.8 plus 0.001093. So total you are getting 0.33135 kg, sorry, meter cube per kg, and we have 10 kg. So P2 is equal to into 10, 3.31 3.3135 meter cube. So total volume after the chamber has been removed, the partition has been removed, is 4.42895 is 7.7 is 7.742496. Are you getting this?
Yes, sir.
Okay. Now tell me what should be the next step. We have to find out the steam quality after mixing. Okay. So we have the total volume, total mass. Calculate total mass is 15 kg. Okay. Total mass is 15 kg. So specific volume is after mixing is divided by 15, 0.5161 meter cube per kg. Okay. Now seeing this, tell me whether the quality will increase after mixing or quality will decrease after mixing.
Lies between 1 to 0.8.
Sorry.
Drain extraction, the vessel 1 is x equal to 1 here, but then the other side is 0.8. So lies between 0.8 to 1.
Yeah, preferably. So you were saying that it will increase, right? So let's see. Then what is the next step it should be? So we have to calculate. First of all, tell me, initially there is no, if we use the first law, so del U is equal to, del U is equal to del Q minus del W. Now is there any heat interaction? Is 0. Is there any work interaction? It is also 0. So U2 is equal to U1. That means after mixing, the total internal energy will be staying constant. So just find out what is U2, U1. Now U1 is internal energy before mixing. Internal energy before mixing. So it will be M1 U1 plus M2 U2. So in the first case, M1 is how much it is given? M1 is 5 kg. So 5 into U1. So U1, this is dry volume. So I have to calculate C at 300, at 200, sorry. 200, what is U? Let me check what is UG. 200 is UG is equal to 2529.1. 2529.1 plus M2 10 into U2. Calculate U2. U2 you can calculate UF plus XUFG. Calculate. This is a lengthy question, so try calculate this one. UF plus UFG at 500 kilopascal. So you might be confused. So let it be U3. Are you calculating?
2176.5.
2176.5.
5.
Okay. So I am trusting this one. Kilojoule per kg is equal to 2176.5. Now final is, we know 15 into U3 is equal to this much. Let's calculate. So 5 into 2529.1 plus 10. I'm getting 2294. Are you getting the same?
Yes, sir. That the unit is kilojoule per kilogram.
Kilojoule per kg, no?
Yes, sir.
Yeah. So once you get that, you have U3, you have the U3 and V3, specific volume at after, let us say this is V3. Now try to match this with, try to match it with steam table. In which case you are getting somewhat near about that. So just check 2294, no? 2294, 2294.
Two two 9293.1 is available.
2293 is what?
At around so we need to refer UFG or otherwise at
You
liquid.
will see around UFG you see
4 kilopascal. 4 kilopascal.
yeah 4 kilopascal. Somewhat near that it will be the final pressure. Okay, so that you need to do what I will say. You have to do the interpolation. You will take, for example, you have V3. Check V3 whether in a near 4 kilopascal the V3 is somewhat like okay. I think somewhat near if 4 kilopascal you are getting. So that will be your final pressure. And based on that, once you fix that, you can calculate UF plus X UFG is equal to this much, whatever you have, 2294.03. From here you will get X is how much. So steam quality is done. Then the entropy change, that is very simple. Once you get S3, X, then S3 minus, so do it by MS3 minus M1 S1 minus M2 S2, plus M2 S2. Okay. So that will be the total entropy change of the process. Okay, bit lengthy process, I know, but you have to solve like this, or directly you can follow the Mollius chart. As Mollius chart has not been covered in your slides, so I tried to solve it using finding U and then matching with the steam table. Otherwise, you can directly go for Mollius chart, because you have the you can from U you can find out H, from U you can find out H, like U plus PV is equal to H, no? So that you can use and find out H from enthalpy, and from enthalpy you can Mollius chart is basically the curve between H and S. So from there you can find out. Okay. So next question is steam initially at 0.3 megapascal, 250 degrees Celsius is cooled at a constant volume. At what temperature will the steam become saturated vapor? What is the quality at 80 degrees Celsius? What is the heat transferred per kg of steam in the cooling? So this is somewhat same question that we have already solved. So I will just give you the hint. So steam initially is at 0.3 megapascal at 250 degrees Celsius. So let us say this is the, sorry for the curve. So 0.3 megapascal, that means 300 kilopascal. So 300 kilopascal and 300 kilopascal, T saturation is 250 degrees Celsius. T saturation is 133 kilopascal, 133.52. degrees Celsius. But we are given that it is 250 degrees Celsius. So which is more? So that is superheated. Is cooled at a constant volume. So let us say this is the T versus V diagram. So pressure will be somewhat like this. So this is the isobar. So let us say this is 0.3 megapascal line. It is, and this is somewhat like 250 degrees Celsius. Now at what temperature will the steam become saturated? So it is constant volume, it is reduced to here. So it is asking this temperature. How to go for it? You calculate V1. How to calculate V1 as this is superheated? So just go to the superheated table. 300 how much? 0.3 megapascal. So 0.3 megapascal, 500 degrees, 250 degrees Celsius is volume is 0.7 0.71643. 0.71643. This is also equal to V2. So check from the table where the Vg is somewhat near to 0.71643 meter cube per kg. So check the table 0.71, right? 0.71 is 0.7. 0.7 is somewhat between 225 and 250 degrees Celsius. Because at 225 you are getting Vg as 0.793. At 225 degrees Celsius, Vg you are getting as 0.79329. 0.79329 meter cube per kg. At 250 degrees Celsius, 0.71873. 0.71873 meter cube per kg. Okay, so it will be falling somewhere between these two. Okay, and we can say that it will be closer to 250 degrees Celsius. So how do you do the interpolation? Sorry, you want to say something?
Sir, whether we need to refer the saturation temperature table, sir, because the initial temperature is 250 superheated. That the specific volume we have calculated. That Vg value is 0.71643 meter cube per kg. For example, if I am referring the saturation temperature table, it lies between 125 to 130.
Oh, sorry. Okay, my mistake. So I'm actually I saw the pressure kilopascal. Correct. Sorry for that. So I just it is actually not 225 degrees Celsius. That is 225 kilopascal. That is where this problem came. So anyways, it will be somewhat like near that temperature T saturation. At 225, the T saturation is 120.21 degrees Celsius. Correct? 123.97 degrees Celsius.
Yes, sir.
Yeah. So if we go with temperature, so temperature at 120 degrees Celsius, Eg is 0.8913. Correct?
Yes, sir.
And 130 next is 125. At 125 degrees Celsius, you are getting 0.77 meter cube per kg. So it should fall between these two. You have to do interpolation. And do you know how to do interpolation? Huh?
Yes, sir. Yes, sir.
Yeah. So just a unitary method. It is like if you are getting 0.8913 at 120 degrees Celsius, then where you will get 0.873. Sorry, 0.716. 0.71643. It will be somewhat near to, I think, 123, 124. Around that temperature you will get. I think 124 you will get. Just I'll see. Yeah, 123.9 you will get. Desaturation. 123.9. If you directly follow the pressure chart, no, pressure table, you see that at 123.97, the specific volume is 0.79329. Okay, which is lying close to here. So that is why you would be getting somewhat like near to that. Just a guess. You can do the interpolation and you can find out where exactly the temperature. So the first bit is A is done at what temperature? So it is 123.9, somewhat near to that. What is the quality at 80 degrees Celsius? Again, there is a cooling, constant volume cooling. So again, there is a cooling. This is, let us say, 80 degrees Celsius. So this is very simple. At 80 degrees Celsius, find out. At 80 degrees Celsius, find out Vf, Vg. Then find out final volume is equal to Vf plus X Vfg. And you just equate that to 0.7163, 0.71643. Correct? Are you getting?
Yes, sir.
Yeah. So once you get from there, you will get X. So mostly X you will get. I can tell the X that you will get is 0.23. You will get 0.23 as X. So this bit is done. Last bit is what is heat transferred. From the last question we can tell. So it is dou Q. Sorry, dou U is equal to del Q minus del W. So it is cooled. What does that mean? And there is no work. Okay. So del Q is U2 minus U1. So what is U2? U2 is at 80 degrees Celsius. Whatever U2 you will get, U2 is at 80 degrees Celsius. U1 is 250 degrees Celsius. Both of these you can find out from the steam table. Once you get the X, from here you can calculate U2. U2 is equal to UF plus X UFG at 80 degrees Celsius. And U1 is of course the superheated steam. Okay? Got it?
Yes, sir.
Did you understand?
Yes, sir. Yes.
Okay. So that's all for today. We have solved almost whatever numericals were possible based on the things that were covered. And if you have any doubt, if you are solving some numericals and you are facing any problem, you can directly send that photo or the text of that problem on my email ID, and I will be answering you within one day. And if any other doubts are arising, you can directly send a mail in that mail ID, whatever I have given. Okay. So we'll meet again in the next week with the next week lectures. Next week lecture is almost, I think, is the air standard cycle. So we'll also see what are the different air standard cycle and also solve the numericals. Till then, take care. Okay.
Okay, thank you, sir. So, sir, I would like to take your mail ID. Kindly share the
Okay.
slide.
So my mail ID here.
Okay. Okay, sir. NPTEL
Okay.
10, 10, 10
NPTEL 10.
Okay,
Correct.
fine, sir. I
Okay.
noted down, sir. Sir, one small clarification, sir. Sir, whether it is possible to share that uh, answer key for the assignment, because why I am asking in the sense, on the assignment 2, first question itself, isothermal compressibility, as per the definition, I have chosen that answer, but I am getting it is mentioned as it is wrong. In
Which
the
one?
same way,
Sorry, I could not get. Which one?
isothermal compressibility definition, sir.
Okay.
Isothermal compressibility of the gas.
Yes.
So here,
Okay.
as per the definition, minus 1 by specific volume into change in volume by change in pressure
Correct.
when temperature equal to constant.
Okay.
But I have chosen that as a final answer, sir. But accepted
Okay.
answer it is saying that minus specific volume into dou P by dou V when temperature equal to constant. So I don't
Okay.
know which one is correct. Anyway, that's why I want to clarify my doubts with the answer, sir.
Sure.
Meanwhile,
No problem.
with one assignment also, I just did some calculation error, I think so. I want to verify it if possible as per the protocol. Is there any possibility to share the answer key? Means it is very much helpful for all others also. Thank you, sir.
Okay. Okay. Whatever problems you have, you can directly send me. I can send you the answer for
Uh,
that, but I
sure,
cannot
sir.
directly
I have
upload the.
taken the.
Sure. No
Okay, sir.
problem.
Now itself, I will send the mail, sir. I have taken the copy of the problem, and now it is compiled. I will share to mails.
Sure.
Thank you, sir. Thank you, sir.